Logarithmic functions, properties of logarithms. Let's start with the definition of a logarithm. For x greater than 0, a greater than 0, and a not equal to 1, the logarithmic function with base a is y equals log base a of x, if and only if x equals a to the y. The number a is called the base of the logarithm, and a is the base of the exponent. So what they're saying here is y equals log base a of x means the number a is the base of the logarithm. And in exponential form, x equals a to the y means a is the base of that exponent. This should look familiar here. This form here looks familiar to our exponential functions. It's just that the x and y have been switched. So it means that our logarithms are the inverse function of our exponential functions. So let's practice what this definition is. Y equals log base a of x. And just to be sure that you're writing this correctly, I'm going to go elementary on you and make sure you are writing this in the right form. This is an elementary school paper. This a, base a, is kind of like how we do exponents up high, but it's low. It's a subscript. But the x is at the same level as you write log. Make sure that you are making an effort to write it correctly as you do this. Otherwise, it can end up evolving as you write, and eventually you end up with something that is completely different than what is intended. This is completely different from what we started with. So x is not the exponent. X is right on level with y and log, and a is a subscript. So I'm going to make sure we're not doing that. Let's go ahead and see another way to think about this logarithmic function. Now, I'll tell you that a log is an exponent. Okay, so with this, I'm saying the exponent I place on, that's the words that you can use in place of the word log in your mind. The exponent I place on base a to get, this argument of the log is x. The exponent I place on base a to get x is y, or y is the exponent I place on base a to get x. So in exponential form, they said was x equals a to the y. So y is what the log equals up here, right? The log equals y. Well, a log is an exponent, so in exponential form, the y is going to be the exponent on the base a. Base a is there, and that gets us the argument of the log x. So a lot of what we do in logarithms is to be able to convert back and forth between these two forms. Let's go ahead and practice that now. Let's go from exponential form to logarithmic form. Here we'll start with 3 squared equals 9, and we need to rewrite it in logarithmic form. So we know first off we're going to have a log in there, and we need to figure out what that subscript is. Remember, the subscript is the base. the base in exponential form is the thing that has an exponent sitting on it. So the base is 3. And remember that a log is an exponent. The exponent is 2 over here, so that's what the log is going to equal, 2. The exponent I put on base 3 to get 9 is 2. The exponent I place on 3 to turn it into 9 is 2. Here, go ahead and write our log. The base is the thing that has an exponent sitting on it, just like in baseball you have a base there and there's always somebody standing on the base. Okay, so the base is the thing that has the exponent standing on it. So there's your base, log base 4. Remember, a log is an exponent. The exponent we place on 4 to turn it into 1/4 is -1. Here, 5 to the 1 equals 5. Log. The base is 5. Remember, a log is an exponent. Your exponent from here is 1. The exponent we place on 5 to get 5 is 1. Here, the log base is 3. Remember that a log is an exponent. Your exponent then is y. The exponent we put on 3 to get x is y. In example 2, let's convert from logarithmic form to exponential form. You might find doing it this direction is a little bit easier than converting from exponential form to logarithmic. Log base 2 of 16 is 4. So we say that our base is 2. Remember that a log is an exponent, so your exponent is 4. So 2 to the 4th is 16. Here we have log base 10 of 0.0001 equals -4. So our base is 10. Remember, a log is an exponent, so your exponent is -4. And we know that 10 to the -4 is the argument of that logarithm, 0.0001. Here, log base 6 of 1 equals 0. My base is 6, exponent is 0, equals 1. 6 to the 0 equals 1. In example 3, we're evaluating logarithms. So first, write y equals log base 2 of x in exponential form. In exponential form, we have the base, the log is an exponent, 2 to the y equals x, the argument of the log. So use the exponential form right here from part A to find y when x equals 8. So 2 to the y equals 8. 2 to the y equals 8. What kind of exponent should you put on 2 to turn it into 8? That would be a 3. So y must equal 3. Let's evaluate log base 2 of 8. So we're asking, what exponent do I put on 2 to turn it into 8? 3. The same as how we got it when we used exponential form. Now let's evaluate the log base 4 of 1/16. What exponent would I put on 4 to turn it into 1/16? Remember, we put negative exponents on numbers to cause them to turn into fractions. And here, if I would put a square on the 4, it would turn it into 16. So if I put a -2, then that would cause the base 4 to become a 1/16. So the log base 4 of 1/16 evaluates to be just -2. Evaluate log base 10 of 0.001. What exponent would you put on 10 to make it 1/1000th? You can experiment here. If you did a 10 to the -2, that's 1/100. 10 to the -3 is 1/1000, which is this number, 0.001. So apparently log base 10 of 0.001 is -3. Example 4, graphing a logarithmic function. We're going to graph y equals log base 2 of x by graphing the equivalent equation in exponential form, x equals 2 to the y. So what we'll do is pick values for y, and then out will come our x. It's reverse of what we're used to doing when filling out a t-table. We're only going to do this the one time, and it's just so that we can see what kind of a shape we get with logarithmic functions. But it's good to see what the numbers are doing so you know why the graph is behaving the way that it is. So here I have 2 cubed, which is 8. Here I have, if y was 2, 2 squared is 4. 2 to the 1 is 2. 2 to the 0 is 1. 2 to the -1 is 1/2 to the 1, which is 1/2. 2 to the -2 is 1/2 squared, which is 1/4. 2 to the -3 is 1/8. And 2 to the -4 is 1/2 to the +4, which is 1/16. Let's graph this. So we have 8, 3, 4, 2, 2, 1, 1, 0, 1/2, -1, 1/4, -2, 1/8, -3, 1/16, -4. You can see as we go this way, we're just going to get closer and closer and closer to that y-axis. We have a vertical asymptote here of x equals 0. We have a vertical asymptote here of x equals 0. As we go this way, our graph slowly rises, but it does continue to rise without bound. We'll have to make it all the way over to a 16 before we finally make it up to a 4 on the y-axis. So this graph grows very quickly at first, and then it slows down. Now, common logarithms are with base 10. They're used so often that if we don't write a base in there, it's understood to be a 10. So a log base 10 of x is the same thing as log of x. Nothing written there, understood, base 10. Evaluating base 10 logarithms. Using each of the indicated methods, find f of 10,000 if f of x equals log of x. So first, let's write the equation y equals log of x in exponential form. That would be our base of 10 to the exponent y equals x. Now find y when x is 10,000. So we replace the x with 10,000. We're trying to find out what exponent we would put on y to turn 10 into 10,000. An exponent of 1 would give us 10, an exponent of 2 would give us 100, an exponent of 3 would give us 1,000, an exponent of 4 would give us the 10,000. So y is 4. Now let's use technology to evaluate the log of 10,000. Log is right here on your calculator. We're going to put log 10,000, hit enter, and you have the value 4 returned in your calculator. In example 6, we have an application of the pH scale. To simplify measurement of the acidity or basicity of a solution, the pH, which is the hydrogen potential, scale was developed. The pH is given by the formula pH equals negative log of H plus, where H plus is the concentration of hydrogen ions in moles per liter in the solution. The pH scale ranges from 0 to 14. A pH of 7 is neutral. A pH less than 7 is acidic. A pH greater than 7 is basic. Now, if the hydrogen ions in moles per liter concentration for bleach is 10 to the negative 13, let's find the pH level. So we're going to use this formula that they've given us and solve for the pH. pH is negative log of 10 to the negative 13. We can use our calculator to calculate negative log of 10 exponent negative 13. And we get a 13. So the pH is going to be 13. If the H plus for lemon juice is 10 to the negative 2, find the pH level. So again, we're going to be solving for the pH. We have a negative log of 10 to the negative 2. So the pH is going to be 2. Again, you can do that on your calculator. Negative log of 10 to the negative 2, and you get a 2. So the lower levels of pH indicate a more acidic solution. How much more acidic is lemon juice than bleach? So we could take our 10 to the negative 2 and divide that by 10 to the negative 13. And it's simplifying that. We'd have 10 to the negative 2 minus a negative 13, which is 10 to the 11. And 10 to the 11, you'll see, is big. It's basically we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 zeros, a 1 with an 11, with a 1 with 11 zeros after it. So it's hundreds, thousands, millions, billions, 100 billion times more acidic than the bleach. Now on natural logarithms. A logarithm with base e is called a natural logarithm. Natural log of x means log base e of x. This is the same e that we talked about in exponential functions, base e. It's the Euler constant. Natural log on your calculator is right here. You can see the e to the x we used in the last section is underneath of that as the second function of that button. Example 7 is diabetes projections from 2010 to 2050 indicate that the percent of U.S. adults with diabetes, diagnosed and undiagnosed, can be modeled by P of x equals negative 12.975 plus 11.851 natural log of x, where x is the number of years after 2000. Let's graph this function. Go ahead and go to y equals and put that function in there. Negative 12.975 plus 11.85 times 1 times the natural log of x. And always safe to go ahead and close that argument. And let's see, what kind of a window should we put? X is the number of years after 2000, and they're showing they're talking about the projections from 2010 to 2050. So we could go from 0 to 50 or 10 to 50. I'll go ahead and go from 0 to 50 to give us a little wider window, and we'll do a zoom fit. There's the graph of our function, and is the function increasing or decreasing? It is increasing. What does this mean in the context of the application? Well, we do know that diabetes cases is increasing from 2010 to 2050, but it is slowing. You can see that the rate is lowering. So the diabetes cases is increasing from 2010 to 2050, but at a decreasing rate. Now, what does the model predict the percent of U.S. adults with diabetes will be in 2022? What is this number, 2022? It's a year, and x is the number of years after 2000, so that means x equals 22. So we could put 22 in for x here. We could look for 22 in the table, or we could do our trace and type in 22 and read off that screen, and yes, it shows there that the percent is going to be about 23.7%. Now, use the graph to estimate the year in which the model predicts the percent will reach 33%. So we can see it's increasing. We're not going to get quite right on 33%, but that number 33 that they've given you is a y value. The years are the x's, the percents are the y's. So we can go back into our equation editor and just make a another equation of y equals 33 and graph that. Remember, the intersection must be in your window for you to be able to calculate the intersection. And it is, and we have success there. So we see 48 years, and part of another year is the year when the model predicts that the cases will reach 33%. So that's going to be the year 2049. So 48 would take us to the end of the year 2048, and a little bit more bumps you into the year 2049. The Richter scale. Because the intensities of earthquakes are so large, the Richter scale was developed to provide a scaled-down measuring system that permits earthquakes to be more easily measured and compared. The Richter scale gives the magnitude R of an earthquake using this formula. R equals the log of I over I sub O. I is the intensity of the earthquake, and I sub O is a certain minimum intensity that is used for comparison. In example 8, we deal with the Richter scale. If an earthquake has an intensity of 10,000 times that minimum intensity I sub O, what is the magnitude of the earthquake? We can figure this out. The R is going to be the log of 10,000 times the minimum intensity divided by the minimum intensity, which is the log of 10,000. And the log of 10,000, if you want, you can put into your calculator, is going to be 4. So this would be a 4.0 on the Richter scale. Show that if the Richter scale measurement of an earthquake is K, then the intensity of the earthquake is I equals 10 to the K times I sub O. So we can do this by saying R is now going to be K equals the log of I over I sub O. Now I change this to exponential form. 10 to the K equals I over I sub O. If I clear my fractions by multiplying both sides by I sub O, then I would have 10 to the K times I sub O equaling I. An earthquake that measured 9.0 on the Richter scale occurred in the Indian Ocean in December 2004, causing a devastating tsunami that killed thousands of people. Express the intensity in terms of I sub O. So here we simply take our 10 to the K being 9 times I sub O. That will be our intensity. And we use our calculator. We have a 10 to the 9, and there we go. The intensity is going to be it'll be 10 but with 9 zeros. So it'll be a billion times the intensity of that minimum intensity. Now if an earthquake measured 7.0 on the Richter scale, give the intensity of the earthquake in terms of I sub O. And how much more intense is the earthquake in part C than the one with the Richter scale measurement of 7.0. So we have 10 to the 7th times the minimum intensity is going to be the intensity of that earthquake, and 10 to the 7th is going to be 10 million. So how much more intense is the earthquake in part C? Well, we could take that and divide by the 10 million. Make sure we have the right number of zeros. 1, 2, 3, 4, 5, 6, 7. One too many zeros, so I'll delete one. And it's 100. 100 times more. And you can see that in the exponent as well. That's 1 power of 10 and another power of 10. This is 2 more powers of 10 than this one. So 10 squared is going to be 100 times as intense. So it might seem like a 7.0 on the Richter scale and a 9.0 on the Richter scale, that those numbers are fairly close, but it's so we're not having to deal with all of these zeros and counting all the zeros. That 9.0 Richter scale rating is 100 times more intense than a 7.0. If one earthquake has intensity of 320 times ISOBO and a secondary has the intensity of 3,200,000 times ISOBO, what's the difference in their Richter scale measurements? In other words, what power of 10 are they different? This intensity is 10 times this intensity. So the Richter scale is going to be 1 power of 10. It'll be 1 in the Richter scale difference. And that does it for this section. Go ahead and try the homework. Let me know if you have questions.